Alrighty, so we're going to look at the second example now, which is our geometric style of optimization. Okay, and this is usually where you're given some form of a shape or a combination of shapes, and you're asked to find, you'd be given a perimeter or an area or a volume, and you'd be asked to find the max or the min of another, of that shape or something like that, or a different concept. So I'm going to give us, there's a lot of blokes you'll learn in maths, there are a lot of blokes building fences on rivers or next to someone else's fence, and they've got only a set amount of fencing they can use. So this problem comes up a whole bunch, so I can only assume that in the real world there's heaps of blokes with 70 metres of fence that can't buy any more, trying to build fences on rivers. Okay, and that's what determines the size of their property. But like with all problems, alright, I've drawn the diagram over here. I might change it to 60, I might get 80 because you've got a 60 in your book or something, but that's right. So you've got an 80 metres of fence line. Okay, he's got three sides, and that's what you're given in the problem. So obviously there's a bit of hidden information that we need to try and deconstruct or digest. So the first thing we know is that our perimeter, and this is, I often like to write down what we have. Okay, let's assign the vertical side. So let's assign this side as let's just call that width, and let's call this side length. Okay. So our perimeter function clearly has two components. So perimeter equals 2 width plus 1 length. Interesting. We know that area, so we know that that shape there is a rectangle. Area equals width times length, or length times width, whichever floats your boat. And somehow we need to get an equation that finds us the maximum area. Okay, so we need the maximum area. We need to use that. So automatically I can see that I've got two functions there. Okay, I'm going to know that I need my function area to be derived, but the problem right now is that I have two variables, width and length. So I need to get rid of one of those variables. So the way that I do that is I look at my perimeter function here. Now right now that's no good to me because I've got three variables in a function, but I know that my perimeter is 80. So I can rearrange that or rewrite that equation instead as 80 equals 2w plus L, and then I just like to pick one variable to get by itself. I'm going to pick L to get by itself, it doesn't matter which one, and I'm going to use simultaneous equations. So I'm going to call this equation 1, and I'll call this equation 2, and I'm going to use substitution. So I've got 80 minus 2w equals L. I'm going to sub 2 into 1. Obviously I'm subbing this version of 2 into 1. Okay, and I get A equals W times 80 minus 2W. So straight up, and I'm going to come back over to this side of the board. Straight up I can see that now my equation area has only got width in it. I'll rewrite it so we know what's going on, which I'll write as 80w minus 2w squared. Okay. Now again I want to find the max or the min. The way that I do that is I'll derive it. Let that equal 0, but I'll derive it with respect to w because that's the only other variable I have in my equation now. So dA dw, which means the change in area with respect to the change in width, equals 80 minus 4w. I let that equal 0. 0 equals 80 minus 4w. Take the 4w over the other side. 4w equals 80. W equals 20. Cool? So I know that my width is 20. I can come back and find my length later, but let's find out if that's a max or a min. So to find if max, I need to use another test. I can use my graphing, or I can use my double derivative. I'm going to use my double derivative because it's easier. D squared A dw squared equals negative 4. Therefore, we have a max, which is good, that's what we want. So we have a maximum, okay? We don't have any boundary conditions to check, so we know that we've got a maximum. We know that that's our value for W. Now we need to find our value for A. and for length. Okay, so I might even just come back to the middle here and rub these sections out above. I'm just going to rub this stuff out because I'm not far off finishing. So I know my W, I know that it's a maximum. Now I need to find my length, and I need to find out my area. So I know that perimeter equals 2W plus L. I know that that's 80 plus or equals 2 times 20 plus L. 40 plus L equals 80. L equals 40. And now I know my area. Area equals width times length, which equals 20 times 40, which equals 800 meters squared. Obviously, that is the max area the farmer can create with that type of fence. So the key takeaways here, the differentiation, the finding the mean, that's not hard. That's something we're very familiar with. The real challenge in this problem, and the real challenge in most of these geometric optimization problems, lies in these first few steps. Creating our equations, using simultaneous equations, rearranging to ensure we only have two variables in our equation that we can derive with. If we've got three, if we've got A, W and L, we can't do this problem. We need to ensure that we've only got A and W or A and L. It doesn't matter which one, as long as we've got one of those variables by itself. These problems get a little bit trickier as we go further, but this is a good starting point to get going.